Hi viewers, welcome to Do Math. So now matrices low remaining concepts. That means adjoint to determinant and cofactors, special types of matrices. What going to discuss చేద్దాం. So first of all, I can take the 3 by 3 matrix A1, B1, C1, A2, B2, C2, and A3, B3, C3 of order 3 by 3. 3 rows and 3 columns. So I can substitute it is A. Okay. So A is a matrix of order 3 by 3. So first of all, I can discuss the minor. So minor means we have 9 minors. So every element has a minor. What you can do this, suppose minor of A1 I can find now. You can eliminate the row and column in which the element is present. So eliminate the row and column in which A1 is present. That means I can eliminate first row and first column. So we have a 2 by 2 matrix B2 C2 and B3 C3. The determinant of the 2 by 2 matrix is called minor. So this is minor of an element. Now and then cofactor. Cofactor of an element. So minor of an element multiplied by minus 1 power I plus j. Minor of an element is multiplied by minus 1 power I plus j. That means I is represents the row number and j is represents the column number. Minus 1 power I plus j into mij. Now the cofactor of a1 is minus 1 power. So a1 is lies in first row and first column, and a minor value is b2 c2, determinant of b2 c2 and b3 c3. So this is called cofactor of an a1. So simply we can denote minor as mij and cofactor as aij or a. So we can denote a1. So because a1, small a1 and capital A1. Now cofactor matrix. Cofactor matrix. That means elements replaced by the cofactors. So these are A1, B1, C1, A2, B2, C2 and A3, B3, C3 are the elements. You can replace the cofactors. In place of elements. So this matrix is called cofactor matrix of A. Cofactor matrix of A. And then determinant. Determinant. Sum of the products of the elements with corresponding cofactors. Sum of the product of the elements with corresponding cofactors. So now I can take A1, first row, first column element, and which cofactor is capital A1. So I can take B1, first row, second column element, and cofactor, it corresponding cofactor is B1. C1, I can take the element in first row, third column, and corresponding cofactor is C1. So product of elements with corresponding cofactors, and this sum value is denoted by determinant of a 3 by 3 matrix. Right? So I can briefly explain minor, eliminating row and column in which presents the determinant of the remaining 2 by 2 matrix is called minor, and minor multiplied by minus 1 power I plus j is cofactor. Elements replaced by its cofactors in the places of the elements, it is called cofactor matrix. And sum of the products of the elements with the corresponding cofactors in any row or any column. You can take any row, any column. So I can take first row, first column. Suppose I can take third row. Third row elements are A3, B3, C3 and cofactors are A3, B3, C3. That means A3, A3 plus B3, capital B3 plus C3, capital C3. So which is denoted by determinant. Okay, right? So some properties of determinant we can discuss now. Suppose, so this is the original determinant. Now I can change the first row and second row. That means interchanging of the two rows, R1 and R2. R1 and R2. Or C1 and C2. So we can interchange the rows, any two rows or any two columns in a determinant. The determinant sign will change. That means positive value can convert into negative and negative value convert into positive when interchanging the rows or columns. So sum of two elements in the first determinant, first column, sorry. We can express as sum of two determinants. First elements as first column and second elements as second column. Remaining two columns are as it is. So which is another property. So in any row or any column, sum of two elements is there. We can write sum of two determinants like this. So this is another property. Suppose product of two values is there, determinant of AB. We can write it is det A into det B. And transpose of the matrix. The determinant of the transpose of the matrix is equal to determinant of the original matrix. This is another one. And determinant of A power n equal to det A power n, where n is a natural number or positive integer. So det of k into det A. So determinant of Ka, that means scalar multiplication of A is k power n into det A, where n is order. So like we have some properties we can discuss. So in the problems we have another models are there. So some important properties I can discuss. And then adjoint of a matrix capital A. It is denoted by adjoint of A. So this is the notation, adjoint of A. What is adjoint A? The transpose of the cofactor matrix. Cofactor matrix యొక్క transpose value is called adjoint A. Okay, I will continue. Cofactor matrix. Transpose of the cofactor matrix is called adjoint. Suppose the cofactor matrix is A1, A2, A3, B1, B2, B3, C1, C2, C3. Then this transpose is called. So interchanging the rows and columns, which is transpose. So this is called adjoint A. Transpose of the cofactor matrix is adjoint A. And now I can discuss inverse or invertible matrix. So what is inverse? If AB equal to BA equal to I. If AB equal to BA equal to I, where A comma B are same order square matrices. Same order square matrices. Then we can write A inverse equal to B. So when it is A inverse equal to B, we have AB equal to BA equal to I. So this is inverse condition. And whenever is inverse is exists now, when det A not equal to 0. Now det A not equal to 0. That means non-singular matrix has a inverse. Non-singular matrix has a inverse. So if det A equal to 0, those matrices are singular matrices. So it has no inverse. It has no inverse. Right. And now we can discuss the properties of adjoint. A into adjoint A equal to adjoint A into A equal to always a scalar matrix which is det A into I. So which is a scalar matrix. Scalar matrix means non-diagonal elements are 0 and diagonal elements are det A equal. So always a scalar matrix. And then I can write here A into adjoint A by det A equal to adjoint A by det A into A equal to I. That means it is in the form of AB equal to BA equal to I. So simple. When AB equal to BA equal to I, A inverse value is B. What is B here? This one, adjoint A by det A. That means the formula of A inverse is adjoint A by det A. So this is the formula for adjoint A by det A is A inverse. So you can observe it in the denominator we have a det A. So which det A equal to 0, that means something by 0 is not defined. That means det A should be not equal to 0. That's why you can say when A is a non-singular matrix, inverse exists because of this reason, right? And I can go with the next one. Det of adjoint A, determinant of adjoint A is det A power n minus 1, where n is order of the matrix. N is order of the matrix, one of the important formula. And adjoint of adjoint A, so which is equal to A power n minus 2 into A. Here also n is order. So small n's represents order always. And I can write in order. So I can repeat the value n times. That means adjoint of, so on up to r times. We can find the determinant of this one, which is det A power n minus 1 power r. That means adjoint is running r times, it is n minus 1 power r. So we can simply write this formula adjoint of adjoint A, that means which is running 2 times. So det A power n minus 1, r value is 2, that means n minus 1 whole square. So this is adjoint of adjoint A, the determinant value is det A power n minus 1 whole square. So where n is order of the matrix. And adjoint of identity matrix is again a identity matrix. Adjoint of A inverse, I can write simply it is adjoint A whole inverse. And determinant of A inverse is nothing but det A power minus 1 or it is 1 by det A, because det A is a real number, right? So 2 power minus 1 is 1 by 2, right? So like that, det A power minus 1 is 1 by det A. That means det of A inverse is 1 by det A. That is one more important point. And then we have A transpose whole inverse. transpose whole inverse. Nothing but it is A inverse whole transpose. We can do transpose and then find inverse. It is same as we can find A inverse and then transpose. Those two values are equal. So like that, suppose m is any natural number, a power m whole power inverse. That means am whole inverse is nothing but a inverse power m, where m is a natural number or positive integer. And AB whole inverse. AB whole inverse is nothing but B inverse A inverse. B inverse A inverse. And those are some important properties we can use for the solving many problems. So now I can divide matrices as determinant, determinants, adjoint, inverse. This is one concept. Linear equation is one concept. That means only two concepts is there. And then I can discuss some important special types of matrices. So types of matrices lo most important and repeatedly we can use in main sum. So what is sambandhinchi? One of that value is orthogonal matrix. Orthogonal matrix. So what is orthogonal matrix? That means if A is a square matrix and A into A transpose equal to A transpose into A equal to I. So if A is a square matrix and which satisfies this condition, then it is called a orthogonal matrix. Now it is in the form of A into B equal to B into A equal to I, right? So what is the value? A inverse equal to B. And now where B is A transpose, right? So in other words, A inverse equal to A transpose. That means inverse of the matrix is transpose of the matrix. That matrix is called orthogonal matrix. So if A is a orthogonal matrix, I can say A is orthogonal matrix. Suppose A is A1, B1, C1, A2, B2, C2 and A3, B3, C3. So which is a orthogonal matrix? We have three properties. So that means sum of the squares of the elements in any row or any column. I can take the first row elements A1 square plus B1 square plus C1 square. It should be 1. That is 1 point. And sum of the products of the elements with two rows or two columns. That means A1 A2 plus B1 B2 plus C1 C2. It should be 0 always in any two rows or two columns, irrespective of rows and columns we can choose. And determinant of the orthogonal matrix is plus 1 or minus 1, plus or minus 1 always. When A is a orthogonal matrix, then determinant should be plus or minus 1. Okay, so this is about orthogonal matrix and very important, right? Repeatedly used in mains. And the next one, idempotent matrix. So if A square equal to A, square of the matrix is again A, then the matrix is called idempotent matrix. So if A is idempotent matrix, then A power n is A and B power n is B, where A comma B are two idempotent matrices. Now A power n plus B power n, it should be written as A plus B, right? A power n plus B power n is A plus B, nothing but A square plus B square equal to A plus B again. So we can take any n value in that formula. If A is an idempotent matrix and I minus A is also an idempotent matrix, that means A square equal to A, then I minus A whole square equal to I minus A. So that is the property. A is idempotent, I minus A is also idempotent matrix. So these are some useful conditions. And if A comma B are two matrices, if AB equal to A and BA equal to B, so where A comma B are two square matrices of same order, this property is satisfied. AB equal to A and BA equal to B. Then A comma B should be idempotent matrix. That is one of the property. Okay. And we can do next. Next to involutory matrix. So if A square equal to I, when square of the matrix equal to idempotent matrix, sorry, identity matrix, A square equal to I, then A is called involutory matrix. That means I can write it is A into A equal to I, right? So that means AB equal to BA equal to I form. So nothing but A inverse equal to B. Here B is again A. That means if a matrix has itself inverse, then it is called involutory matrix. And the determinant of the involutory matrix is 1, minus 1 or plus 1. Okay. So this is one of the result. If A is involutory matrix, then determinant should be minus 1 or plus 1. It is compulsory. And the next one is nilpotent matrix. So nilpotent matrix means A power P equal to 0 for some positive integer. Then A power P equal to 0. If A is a square matrix and A power P equal to null matrix for some positive integer, then A is called nilpotent. And the least value of P is called index of nilpotent matrix. Least value of P is called index, right? And now suppose A square equal to 0, then highest powers of A cube, A power 4, A power 5 and so on, all equal to 0. If A square equal to 0, so that the least value of value is 2 here. That means 2 is index of A. So that is importance of index. So when A power P is 0, then it should be A power P plus 1, A power P plus 2, A power P plus 3 and so on, all are equal to null matrices. The least value is called index. And here determinant of nilpotent matrix is 0 always. If A is a nilpotent, then determinant value is 0. And one of the property trace of A, that means trace of a nilpotent matrix is also 0. What is trace here? Sum of the principal diagonal elements in a matrix is always 0 when it is a nilpotent matrix. So this is about a nilpotent matrix. Those are the some important concepts. So this is theory class only. So you can revise it. Some important formulas I can discuss. Okay. Take care all of you.